Hello, everyone. Good morning, good afternoon, and good evening to all. I am Liji, Senior Data Scientist with the Tata Consultancy Services. With me, my colleagues Mathumitha and Boobalan will be sharing the presentation today. Today, we are going to present the topic the Searchable Grid, building a GraphRAG-powered digital twin. In this session, we will explore how we transform traditional electrical grids into intelligent searchable system using knowledge graph and GraphRAG. Let's see the agenda for today. Next 30 minutes, we will deep dive into GraphRAG powered digital twin for electrical grids. So first 15 minutes, we will be covering the presentation. After that, we will go to the live demo. So we will be starting with the challenge or the problems which you are facing in the utilities. After that, we will see the proposed solution. Then we will move to architecture and data model. After that, we will go in depth of GraphRAG implementation. Then we will see the real world use case on fault tracing. Finally, we will conclude with the deployment and live demo. Let's begin. Let's take a simple scenario. There is a critical system alert. Fault is detected at substation X. Customers are losing power. We wanted to know how many customers are impacted, where they are located, what is the restoration time. In the current reality, how much time it will take? Any guess? So in the current reality, it might take 30 minutes to 2 plus hours due to the manual tracing and multiple system lookups. So in this proposed approach with the GraphRAG, we will get the response less than 5 minutes, sometimes in 5 seconds as well. So here we are applying instant topology query and connected customer counts. Let's see more details about this. What are the challenges current utilities face? So here we are concentrating on one particular problem, static grids in the dynamic world. Let's see more details about this problem. What are the current limitations here? Static diagrams that don't reflect real-time conditions. Also, disconnected system create data in silos. Moreover, slow decision making due to manual data integrations. Also, limited diagnostic capability for complex issues. Engineers work with the outdated diagram that doesn't show the current conditions or the live update. Electrical networks generate massive data from GIS, AMI, asset health, and DER. As per the current study, 70% of the data remain unanalyzed. So how we can mitigate this problem? What are the solutions available? Let's see one of the proposed solution here. We are proposing here a searchable intelligent digital twin. So in this proposed solution, a transformative approach using Neo4j knowledge graph combined with the GraphRAG to build a searchable intelligent digital twin for the distribution grids. So the solution contains main three components. First one is the unified knowledge graph, then GraphRAG intelligence layer. Moreover, we are having in natural language queries. So in the unified knowledge graph, distribution assets unified into a single semantically rich knowledge graph. The assets contain substations, feeders, switches, transformers, smart meters, etc. We can configure any asset into our unified knowledge graph. Once we build the semantically knowledge graph, then we will build GraphRAG intelligence layer on top of that. So here we can dynamically retrieve relevant subgraphs. It identifies historical patterns. It incorporates real-time state. Also, it's provide contextual explainable answers. And we are adding in natural language queries on top of that. Because of this, it helps engineers and operators to ask complex domain-specific questions in a plain English language. For example, show me all the customers affected by the fault at substation X. Plain language, we will get a quick response less than 5 seconds. Why we choose GraphRAG here instead of RAG or machine learning or deep learning? What are the benefit of GraphRAG? Graph is having native relationship. So we can use direct pointer based connections instead of expensive joins. Also, it's having multi-hop traversals, constant time pathfinding regardless of its depth. Moreover, it's having a dynamic topology. So no reconstructions needed for network changes. And Neo4j GraphRag have a built-in graph algorithms like pathfinding, community detections, etc. That is the reason we went with the GraphRag. Let's see the architecture. So here we are proposing GraphRAG-powered digital twin architecture. So it provides real-time, explainable, and intelligent grid operations. So this is a five-layered architecture. So it started with the data ingestion layer. So here we will have various data sources. See, all the data will be reaching to knowledge graph through streaming or batch process based on the needs. So in the knowledge graph layer, in based on Neo4j, we will be building assets, topology, temporal, events, and customer information. So our this is the semantic informations will be available in our knowledge graph. Once the knowledge graph is ready, we are building a GraphRag and AI layer on top of that. So here we will have a retriever graph traversal based on cipher and vector search. Then we are having a knowledge index. So here we are doing an embedding on nodes, edges, and the time windows. Then we are having a RAG engine based on LLMs and reasoning for the explainable contextual answers. After that, we can add ML models for prediction, forecasting, or anomaly root cause analysis. Once the GraphRag is ready, on top of that, we are having a digital twin application layer. So here we will have real-time operations, outage impact, what-if simulations, and natural language processing. Finally, we are having a dashboard and API. So here we can have operational dashboards, 2D or 3D visualizations, API and webhook. If required, we can add a mobile alerts as well. So this is the end-to-end query flow. User will be providing any query, basic English language or any language. Then it will go to GraphRag and it will process the information. It will identify the reasoning. MN analysis will be performed. A response will be generated. Finally, the action will be available in the front end or the dashboard. Hope it is clear. Next, we'll see one of the use case. So this use case, Madhu will be providing more details. Madhu, handing over to you.
Thank you, Liji, for clearly walking us through the challenges on GraphRAG-powered solution. Good morning, good afternoon, good evening, everyone. I'm Mathumitha, data scientist from TCS. I will be taking you through the practical side of the solution, how it actually works with the real-time scenario. So in this section, I'll walk you through the real-world scenario, fault tracing and propagation analysis, and demonstrate how our GraphRAG-powered digital twin enables faster, more intelligent and decision-making. Let's dive into the scenario. Let's consider a very common and critical scenario. In this, now when a fault happens, engineer need to quickly answer few key questions. Which customers are affected, how the fault propagating, where we can isolate it, and how long the registration takes. Traditionally, answering these questions involves navigating to multiple disconnected systems, which both time consuming and error prone. So now let's look how the scenario is handled practically. So with the GraphRag, the interaction starts with a plain text, a simple language. As you can see, show me all customers affected by the fault at a substation X, along with the details and estimated registration time. So behind the simple query, multiple intelligent processes are triggered. First, it understands the query and retrieve the subgraph, graph traversal, contextual enrichment, and finally we get a response. So on the right hand side, you can see the total response, how long it would take to get the 1,247 customers have been affected, and the registration time is given based on the real-time data. So now let's move how a query is being answered here. First, the system will try to understand the intent of the query. Here, the key entities are substation X, and the objective is the impact analysis. So now this is fed into a parsing question. So it retrieves a relevant subgraph from the knowledge-based Neo4j knowledge graph. So this comes to the traversal, where the system traverses the actual electrical fault path, moving step by step and fault source downstream through all the connected components. At the same time, the system performs a contextual enrichment. Not only the connectivity helps in this, we also need the properties. So properties and the real-time examples help us more to provide a better solution. So finally, it generates a response that's not just a data, but a clear, structured, comprising the unstructured as well as a structured data, listing affected customer, listing the affected. Along with that, we have a traversing techniques. It can be a simple traversal or the multi-traversal, multi-hop. And finally, it generates a response that is not just a data, but a clear, structured, explainable answer listing all the affected customers. Now, if we compare with traditional approach, engineers would manually have to gather the data from multiple layers, cross-reference diagrams, and validate the connections. So this would typically take around 2 hours and is highly dependable, and expertise is required to do that. So with GraphRAG, same outcome is achieved in very lesser time. Significantly higher the accuracy and more completeness. So what we're really going to do here is transforming a complex multi-step engineering task into a single intelligent query. So at the heart of the GraphRAG, the processing pipeline, now we are going to try to connect architectural flow with the use case. So initially the fault detection happens. The SCADA system will get a trigger in the dashboard to the end user. And what happens here, the substation X is being identified through the natural, it has to be identified. What we have to do, an engineer will give a natural language query, and then it will flow through the GraphRAG pipeline. So as we saw earlier, parsing, user will give the query and identify entities, traverse the graph, enrich with historical and real-time data, finally get a response. And then historical events will help us more to identify, to check the pattern, how long the registration will take. And the response will also be in a contextual mode, in a simple language. So this is a Neo4j schema. This we have adapted. It's based on the IEC 61968 common interface model that is representing a distribution side. How the model has a core assets like substation, feeder, transformer, breaker, and the electrically connected networks. And it starts from a major geographical region, and then it has been divided into many sub-regions, and the major assets are being connected with their relationship. It's also connected with their asset properties like voltage, capacity, status, along with the measurements, that is the real-time data, till the smart meter. So aligning with this standard, the model ensures standardization, interoperability, and realistic digital representation of the grid. So one of the key aspects here is text to cipher translation, how it happens. So LLM helps in this. User would ask a question in a plain English text. LLM would translate it into a cipher query that is machine understandable, post which a query runs in a Neo4j graph and results are converted back into human readable language. So these are 3 examples that is being shown here, where each for example, show me all the customers affected by fault at substation X, how the cipher query is built, and what is the hosting capacity of a transformer X at feeder Y, and which customers affected by a fault bus, the primary bus 60. So these are the different ciphers. Now let's take a look at foundation, the graph data model, substation, feeder, transformer, smart meters. These are all the major entities, and how the properties are aligned is being listed below. And the most important relationship will between them will help us to give a semantic rich model that allow us to model not just the data, how everything is being connected and behave from a different source. So for this implementation, we used the IEEE 123 bus system as a benchmark, which gives us connectivity along with that real-time data from SPEN. And combining both, we generated a synthetic data on top of which we are working on. We are going to show you a demo. So this helped us to simulate a realistic behavior, validate fault tracing, accuracy, query performance, and scalability. So this demo will not only give you a solution as a theoretically, it also provide you a practical viable thing. So this flow shows the from where the schema starts. So geographical region, and it moves to sub-regions and to a primary substation. From there, power flows to a feeder distributed electrical network. From there, the high voltage is being from 132 kV till the downstream at 0.4 kV. So this is the flow, and it has been transferred at every level by the step-up transformers, along with the path components like breakers, switches, and busbar that also helps to control and manage the flow. What's more important here is every connection is explicitly modeled in Neo4j using the relationship. So instead of interfering the connectivity, we can directly traverse through many algorithms that helps us to retrieve data from a very complex network and identify where the root cause and the fault has occurred. So the next data set is the similar thing. First, at IEEE, combining both IEEE model, we have made a utilized the standard benchmark representing the real world distribution. This gives us a reliable structure of testing it. Second, we used a synthetic real world that includes a realistic grid behavior. So this flow here is a data is ingested from these sources, converting into a graph model. Then they also enrich relationship and properties. So GraphRAG what help us to perform accuracy, speed, and scalability. So overall, this ensures our solution is not just conceptual, but also validate practical, realistic data. So this is the environmental setup. And the backend, we are making use of Python and Neo4j database for the knowledge graph. And for embedding, we are making use of NVIDIA. And for LLM, we have tried with multiple LLMs, Gemini, NVIDIA, ChatGPT, DeepSeek. The most prominent one will be shown for the demo. For a better understanding for the user perspective, we have created a GUI using Python, HTML, and a unicorn web service that includes JavaScript. Over to my colleague, Boobalan. He will show you a live demo on this. Thank you.
Yeah, thank you, Madhu. Thank you. Lijik, can I stop sharing?
Yeah. Yes. You can proceed.
Yeah. So, thank you all. So this is Boobalan from TCS. I'm technical lead. I'm leading the Neo4j and GraphRAG and the ML. So thank you. Here, thank you, Madhu and Liji. So in this our solutions we are covered. So the architecture and other perspective and how it is working, everything is there covered. So I'm going to cover for the data and how it is working and embedding how we are done and some samples also we are going to demonstrate. So in this we are getting the data is in our solution. The data source is multiple power system repositories, and there's include the substation master and feeder from the outage and the events details also we are loading in Neo4j. Each data source contributing the critical piece of information and helps us to understand that and how the electric field from the substation to end the customers. All these data sets we are ingesting and we're creating that unified power distribute system network. These data source it's provided both structure and semi-structure and IAC standards, whatever we have that we are provided to LLMs. We get it that simulated data from that LLM. So that the data after receiving the data, we are providing, we are doing some cleansing and pre-processing we are doing in that data, then we are importing in Neo4j side. So these data we are using in Neo4j side. So you can see data samples and also all the assets, whatever the power transformer low, voltage level, and the energy consumer, AC line, and the transformer, and feeders and switches, all the information will come. And apart from measurement, what exactly that assets is going to provide, that information we are getting the measurement table, and time series data. So all the assets, what is the current flow it's happening. So those informations we are getting and we are generating from each 15 minutes. We are loading that data in Neo4j. So this data source we are using. So in Neo4j side, we are creating the schema. That schema getting. So in Neo4j, so we are using this SIM IEC standard schema we are replacing. So this which is widely adapted to in the utility domain. So in our knowledge graph,
Boobalan,
we have the substation.
uh,
Yes.
Boobalan, can you come little near to the mic? Audio is
Okay.
visible. You can be little
Okay.
loud. Yeah, thank you.
Okay. Yeah. Yeah, our knowledge graphs, we have the substations and feeder transformer assets. We have them apart from measurement and voltage levels, and these assets we are maintaining in the nodes, and power flow and other connectivities we are maintaining in the connectivity sites. The relationship we are using. So using SIM standards, we are considering that models. It's consistentable and reusable and efficiently we extend to further futures systems like a SATA system and other system we can use it. So now you can see our knowledge graph. This here you can see this is a starting the region sub-region. So here you can see the substation. It's a secondary substation. So secondary substation, what are the assets are connected, so that you can in the real world we are connecting disconnector breakers and the switch LBS. Those information will connect, and apart from that feeder also, it will connecting the power system and the power transformer. So this is for the AC line segment. It's AC line segment, it will connect for packet stations, and packet station will connect the LVDB and the measurement, and the finally it's the consumer will consume the data. So and what the measurement it's going on, and the measurement, each measurement, what values we are maintaining, all the information we are maintaining in the measurement value nodes. I will show that our database 1 minute. So here you can see around 4,71,000 plus nodes we are maintaining, and the relationship also same, and 100 pluses of properties we are maintaining in Neo4j. So here I show this, some nodes. Here this is the feeder. So these are the informations we are maintaining in the feeder details, and the feeders, how we are created that embedding. So all the property informations we are accumulating, and we are creating the JSON. That JSON we are traced into NVIDIA, then NVIDIA embedder. So NVIDIA embedder is created the embedding this embedders code, and it will we are updated in Neo4j nodes. Here you can see that feeders, how many assets are connected. So you can, you know that the feeders have the line connectivities, and feeders have that LBG switches, and load breakers and current limiter, and those many electrical terms assets will come, and the connectivity is coming from that primary stations to feeder. So and feeder have that switches. So switch line. So line we have the other in. So all the informations whatever it's generated things. And apart from here the measurement values, so we are maintaining. So in the measurement we have that all the suppose you the transformer, we have that transformer, we have that measurement. So in the measurement for the transformer, what is the 50 minutes load it's happening. So those informations we are getting this each 15 minutes load we are loading in Neo4j. So this is the data set we are loading in or maintaining in Neo4j for this demo purpose. So now I'm going to walk through our demo. So we are use case for fail detection and restoration for that we are use case. In this demo I will show that simulated substation and the informations whatever we have, that when the substation is status is changing, so that time the status changing, so that time how many customers will affect, the affected customers, how do we can resolve that issues, and what is the nearest feeder or adjacent substations, so what is that nearest place, and to restore that issues and prioritize the restoration activity and reduce the outage timing and durations and minimize the customer impact. So that the reason, so they're utilizing these models. And so here we are using that Neo4j. In this demo, we are utilizing Gemini A and the NVIDIA in the particular main fully we are using. In here Neo4j, we are maintaining that 1000 to for that the dimension and the question similarity we are using. So I will show in Neo4j as well. So we are maintaining that labels and labels details. Apart from that, NVIDIA based we are created the dimension and the question details we are created for the index. So they're based on the index only. It's executing and various cases. So I will try to extract this. So this UI, the particularly for HTML and CSS and JavaScript based UI is for the demo purpose we are using. So instead of how it is working, that Neo4j, JavaScript getting that details and sending to GraphRag, and GraphRag is deep drive to index and getting that, and Neo4j then getting that reasoning values and the return back to our GUI. So this is the details we are getting. So how many customers affected the substation for failed transfer? They are the 5,756 customers affected for the files of the stations it goes. So here I also will run that cipher query wise. Also we extracted the same data. So here the accuracy it's are, so it's coming same. So in Neo4j we have that few more feeders here connected in the under the substation, so that all the substation we are summary so, accumulating, and we are showing that customer details. Yeah, I will show other some demo also here. What's the impact the transformer is at risk means. So here, so we are interacting with the knowledge graphs. So I don't know. I know the transformer details. So I need to know that transformer is fail or any impact is happened. So what are the customers are impacting, and which area is available. Those information we are getting from there. So you can see here the substation details we are providing. It's impacting 53 customers in that connected the transformer. The area is South District, and where the substation is connected to grid SS North only. So this way we can interact with our Neo4j. Yeah. Uh, yes, due to time limit, we are winding up to demo. So I'm summarizing for that. So for now, we are complete. We are go through that GraphRag and future and smart grid industry data and architecture, how that GraphRag it's working, and those informations we are explained. And apart from that, we are given some GraphRag with the smart grid industry collaborative one use case scenario and how it is extracting those information we are given. So here and what are the models we are using, that information also we provided. So here's let me go my. Yeah, so the key takeaway is making the grid searchable and examinable and intelligent. So the key feature is the searchable grid, graph rag, and a digital twin could together make the electrical grid truly intelligent. Yeah, thank you for your time, and we are happy to take any questions or discussion on this feature.
We can see a couple of questions in the chat. Due to time limit, we will be responding those questions in the chat. As our time is already exceeded, we will be responding to all the questions. If any additional questions, you can scan the QR code and post it, or you can put it in the chat. We will be responding. Thank you.
Thank you all
Thank you all.
for the opportunity.